السلام عليكم. مرحبا بكم في CNCF مينا العربي Kate's Arabic. We are hosting today Nick. Nick is from On That, and we'll be talking on the series of application modernization, and we'll tackle the data on the application modernization part of it. So basically, we'll tackle what is cloud data, or most likely cloud native data, and we'll leave it to Nick to to introduce himself and to start the presenting. Welcome, Nick.
Okay, thanks very much, Walid. I'm delighted to be there today with you guys. So hopefully it's going to be a fun and interesting session. So my name is Nick. I'm a principal developer advocate with OnThat. I've been there about 6 months, even though it looks like it's been years now. But I guess it's just the Kubernetes, landscape, how it moves quickly. And so yes, Walid, today I'm going to be talking about cloud native data and stateful application, all about databases. So hopefully it's going to be fun. Yeah.
Okay. Do you want to share your screen?
Yeah, sure. We can get started if you want. I don't know if you want to add anything or if we can get
Yes. So
in the weed.
Yeah. So folks, we will have again giveaways. We'll have 3 KCNA vouchers, and we can have also AWS credit. The vouchers are from Andrew Brown and his team at ExamPro. So basically what we will do, we have a form that I will share with you, and we will do a random, basically draw at the end to select the 3 winners. And if you have any questions, you can put it in the form or ask on the chat, please. Thank you.
Okay, so I've shared my screen. I think you have to put it on, right?
Yes.
Okay. So let's get to it. So approximately the talk should be around, I would say 40, 45 minutes, depending on, questions and things like that. I'm going to be monitoring the question on my right. So if you see me looking on the right, it's because I'm going to be checking the questions. So again, the talk for today, we're going to be focusing on cloud native data 101, how to run and play in your stateful application. So basically, whether you're a total beginner into Kubernetes or a more advanced user, storage and persistent data is always something that kind of is left on the side. So hopefully today we can shed some light. But first, I want to address. Actually, the talk is divided into the first part is really talking about how enterprise should run data today, like on premises versus the cloud. And then in the second part, we're going to be focusing more into how to do it in the cloud, but more specifically with Kubernetes as the cloud operating system. So first, I want to address what are the motivations for you as an architect or as a developer or just as a business decision maker, why you would want to build your stateful application and run basically your data inside public cloud providers, services. So here, let's make it clear what we are talking about is basically platform as a service. Things like RDS, or you want to run a database that is managed by the cloud provider. It's not managed by yourself. You manage the data, you manage the application, you manage eventually the middleware, but the data is run by the cloud provider, meaning that it's responsible for the infrastructure, it's responsible for the management, the scale, all of that is provided by the cloud provider. So as opposed to on-premises solution where you have to deploy the database, provision and provide the underlying infrastructure, whether it's disk, servers, network, that costs a lot of money. And if you look at the data center, just hardware refresh rate is probably, I would say, depending on the country, on the region, I'm not sure for MENA, but let's say for maybe US, Europe, what I've been seeing is mostly between 3 to 7 every 3 to 7 years, you have to renew the hardware. I used to work for Cisco, and we obviously also had a lot of customer in MENA. And yeah, typically this 5 years is a good number where you just renew your hardware, right, and migrate some of the stuff you have into this new hardware, whether it's server, network switches, SAN storage. All of that costs money, and obviously you can abstract this layer when you are going into the cloud. So that's one valid reason to build data services into the cloud as opposed to on-premises. So a second one, so we'll be talking about infrastructure. A second one, economy of scale. Of course, you cannot really plan how successful your application is going to be if you're working for a bank and maybe working on a front end or a user-based application, or if you're doing business, a B2B kind of application. Depending on your customer base, how you grow, you may have to scale your database or your stateful application. And so again, if you do it on-prem, it requires a lot of potentially manual action. If you don't have built your private cloud where you enable this self-service provisioning, scalability, elasticity within your data center, then you have to do this all manually, right? So in 2022, it's not savvy to run and operate an application that has scale requirements if you don't have either a private cloud solution, meaning that you have all the automation and the engineering, the DevOps practice to operate this. So it's better to do it in the cloud, because in the cloud, by default, it's going to be elastic. By default, you're going to be having a lot of different DevOps tooling. And another one is also, we're talking about this DevOps tooling, is how you want to integrate your data within your application ecosystem. So again, if you're building an application that is on-prem, well, you can only do with the tools you currently have. So in terms of innovation cycle, it tends to be a lot slower, right? So if you're in the cloud, as soon as AWS, Google, Microsoft release a new set of features, you can start using it as a fraction of the cost of its implementation, because of course the bill is going to be a lot higher for the cloud provider, the hyperscaler, to build the solution that is underpinning the service. But as a consumer, well, you just have to provision the service, 3-click or one command line or just one couple of line of code with the SDK, and off you go, right? You can start to build your innovation by leveraging the hyperscaler innovation cycle. So you stay, very competitive compared to your competitors, and basically it gives you potentially a competitive advantage. And the last one, why you may want to build your stateful application and database in the public cloud, is of course high availability disaster recovery. So for sure, in the past, everyone noticed that it's not uncommon to have issues in AWS or in Google, Microsoft, all of them. So what is the right architecture for you? So of course, you need to have more than one AZ, potentially multi-region if you want to do some sort of load balancing or caching closer to the user. All those kind of things, again, in the cloud, it just makes sense to do it there, right? It's very easy. You can consume all those features quite easily. If you run your own data center and you have an application that is latency sensitive for the user, well, it's not very much a good idea if you have a single data center and your objective is to conquer the world, right? That doesn't really work this way. So yeah, it makes a lot of sense to run data application, and actually why you want to run data close to the application is because of latency, right? The closer you have your data set to the application, the fastest your application will behave, potentially, assuming that you don't have any application issues, like from a latency perspective, you want to avoid the latency coming from the application accessing the data, right? So another thing I wanted to clarify is what we talk when what we mention, or when we mean when we are talking about stateful application, right? So as opposed to stateless, one thing I'm always, saying is that there is no really such thing as a completely stateless application. We've been, working with, especially in Kubernetes, with containers and front end and web application. All of those, at some point, they still need to store some data. What is different between like prior patterns, like 15 years ago, and the patterns we have today with microservices is back in the day where we have this monolith application, usually you only had a very large database, and every team and every service was making use of that particular gigantic database, and then the DBA would manage this large chunk of data into a couple of very large databases. Now with the advance of microservices, what you see realistically when you deploy a more cloud native application is that every team will be responsible for a couple of microservices, and every team and set of microservices will access their own data sets, which means that they will be probably managing their own message queuing solution or their own database, right? So from a large database, we are moving away from that model to smaller and more databases running, and the responsibility is also kind of setting. It's basically an exploded model where the DBA is not like part of a single team. You will find people in every teams responsible for a couple of microservices who will be managing those databases, right? So it makes also more sense for those kind of approach to use the cloud. Again, like whether it's scale up or scale out, it's the same sort of principle. And here I'm displaying the Magic Quadrant for a cloud database management system from December 2021 from Gartner. And you can see that, of course, when it comes to running data in the cloud and moving this center of gravity from your data into the cloud, well, the first ones are obviously AWS, Microsoft, Google, and also Oracle, because of course Oracle does propose Oracle as a service into Oracle Cloud. And what I've seen is a lot customer actually moving to Oracle Cloud for that very particular reason, because they're like a historical customer who have been using Oracle database for decades. So it makes sense for them to move into Oracle, at least for that particular portion of application, right? So now whether the it brings again the question, should I've been talking about potential failure in the cloud, multi-AZ, multi-region, and now I've also mentioned people using cloud for a particular reason. Like you may be running AWS for your standard workload, but for your database, because you're using Oracle, you may want to choose Oracle. So which brings me to the question, at the same time I'm checking if there are any question there. Not at the moment. That's cool. So which bring me to the
worry.
Yep. Yeah, you will tell me. Okay. If there are any questions. Super. So which bring me to the question, should you have a multi-cloud strategy, right? So especially when you want to run data in the cloud, well, you may want to do that, but just do it for the right reason. Just consuming multiple clouds because it allows you, maybe you think, to provide better availability. Although the argument may be correct, the cost versus benefit ratio, if it's only for that, may, because think about this, right? You need to, if you're running into multiple clouds, a database into multiple clouds, you will have to learn all the tool set that comes with it. In the AWS, Azure, Oracle Cloud, I don't know, or Alibaba Cloud, Ali Cloud, all of that. It's like, if you're a developer, it's almost like learning different, programming languages. So if you want to use different cloud just for high availability, it doesn't necessarily make sense just for that. But of course, my personal view on multi-cloud is just happening because not necessarily because of requirements, just because of how the business is run, like mergers, acquisition, or again, if you're a large, Oracle customer and you want to migrate your databases in the cloud, it will make sense to use Oracle at that moment, right? So always think about your use case and the reason why you have more than one cloud. My personal experience is it's not necessarily a technology reason. Most of the time, it will be a business reason. But anyway, long story short, here this is some statement by Gartner, and I I do believe in this prediction where by 2022, which is this year, 75% of all databases will be deployed or migrated to a cloud platform, with only 5% ever considered for repatriation to on-premises. That's quite interesting, right? So this is hyperscaler solution, right? RDS and Bigtable, all those kind of managed databases. Another one, so by 2023, cloud preference for data management will reduce the vendor landscape with the growth in multi-cloud, increases the complexity for data governance and integration. And finally, cloud DBM's revenue will account for 50% of the total database management system market revenue. So what really that shows us is that we're proceeding, we're in the process of migrating all the data into the cloud. So that means that and remember, data is what makes a business valuable. The data and how you use that data for sure. But what that means is the center of gravity is literally moving from on-prem to the cloud. That includes all the adjacent area, security, storage, all that is migrating to the cloud. Compliance, upgrades, all of that all those operational components needs to be migrated into the cloud. So let's go to the next one. But the reality is, or the question we should also ask ourselves is there a better way? Is there a better way? Because I'm not going to lie here, probably a lot of you have experienced this. Like the cloud providers, hyperscalers, you have one meeting with your solutions architect. You say, okay, I've got this problem. Okay, the cloud is always the answer because there's always a service that will match your requirement. But the challenge is, again, maybe that's a good fit for one particular problem, but maybe you have another problem that requires another cloud, or you have you have to make use of another service that is attached to the one you are consuming, and slowly, gradually, you are consuming more and more services, potentially different clouds, and suddenly you have this massive chunk of operations requirement that are falling into the operational team, and you need to adapt all your processes quite fast, right? So as you slowly migrate to the cloud, you also migrate all your IT processes in the cloud. So that's a good thing for the cloud service provider, but maybe that was not your initial thought. And suddenly you have to migrate because the cloud providers, they don't leave you a choice. They don't give you the choice. And again, as I was saying earlier, project number one, this is a MongoDB database. That's fine. You do it in the cloud you're currently using. Second project, you have to go to Google. This is Bigtable. Or you have to use Oracle. This is going to be happening into Oracle Cloud. What do you do with your ecosystem services or your DevOps tools that maybe were running into Azure? Well, now you are in hybrid environment where potentially you will be using DevOps tool from Azure, DevOps tool for AWS, DevOps tool from Oracle. If you're a large customer and you have the knowledge, then that's perfect, right? But again, if you are a smaller customer and have to manage all the things with a couple of people, then the learning curve is really, really steep. So is there a better way to do that, right? So the answer is, in my opinion, yes. But Walid is coming there. Okay.
Yeah, there is There is a suggestion from one of the audience. He's saying for multi-cloud strategy for database, we recommend as a best principle strategy to be no vendor lock-in between them. What do you think?
Yeah, so actually my opinion is exactly what I'm going into, which is instead of relying on the cloud vendor to bring you this kind of standardization, because in the end this is what we need. We need standardization to be cloud agnostic, right? And to do that, rather than using all three of them, right? Because the problem, if you use all three of them, you're locked in three clouds, right? Or more. Like it's still a lock-in because the end solution still depends on the cloud you're using, right? So my preference then, and this is where I'm going, but it's like a teaser, is if you go in any cloud, so whether it's AWS, Oracle Cloud, Google, whatever, they all have Kubernetes managed solution, right? Or that's one, right? So you have in all clouds, you will find a Kubernetes managed solution, and then you can leverage Kubernetes to run your database. And because you have the Kubernetes layer, this is the standardization, because you run it the same way. You run, your manifests, your application manifest, your database operator will stay the same regardless of the cloud. So that's a way to standardize everything. Now, if you even want to bring the standardization even one step further, you can still say, look, EKS, OKS, whatever the name, OKA, I can't remember all the names, they are still proprietary control plane, meaning that you have access to the worker nodes. So there are still some sort of lock-in because you're depending on the hyperscaler to manage your Kubernetes environment. So what you can do is choose a solution like Rancher or OpenShift. But I mean, yeah, OpenShift is probably a bad example because every cloud has also a managed OpenShift solution. So Rancher or similar solution, let's say, where you can essentially, from a central point of management, deploy a standard Kubernetes cluster anywhere. And there you are completely independent and you're not locked in anymore. But you're always locked into something. So in that case, your only locking will be Kubernetes. But Kubernetes is open source, right? So it's better to be locked into Kubernetes than being locked into AWS, right? Because what Kubernetes will cover is much broader, right? So then you can start building all your services inside Kubernetes. So function as a service, you can build your PaaS environment, your DevOps tools. Instead of consuming hyperscaler tools, you can start building them in Kubernetes if you want to, right? I'm not saying that you have to, but if you want to continue to standardize your tool sets, then this is also something you can consider doing, right? Hopefully
Yes.
that makes sense.
Yeah. We'll continue after. It can be a long-winded question, this one.
Okay. But anyway, I've done like some spoiler already of what I'm going to be talking about. So yeah, so basically this Kubernetes approach is what I'm going to tell you for the next half hour. What time is it? Oh, I'm talking too much. Yeah, about 20 minutes or so. So the idea is, if we take a look at these are the most popular container images in the industry. So look at them, and it's like 14 of them. More than half of them are meant for stateful application. Redis database, Postgres database, RabbitMQ. I mean, Elastic has some stateful component. RabbitMQ also message queuing stateful. MySQL, Mongo, Kafka, Vault to some extent, etcd. All of that are already stateful applications. So if those containers are images are the most popular to run in Docker, then obviously they will, have a good play in Kubernetes. That's a good fit into Kubernetes, but not just like that. You need some extra intelligence in Kubernetes to make your database application, and more generally speaking, stateful application, work properly. And this is why I'm talking about Kubernetes as a cloud framework. If you start positioning Kubernetes as your standardization layer, then you can also start making use of the operator paradigm. So the operator ID is essentially to replace some of the database or application operation, like manual operation, by something that is automated. So the idea of the operator or Kubernetes operator is to create automation within Kubernetes. Right? The idea is to extend again the Kubernetes API to create first-class objects. Things like a database doesn't have any existence in Kubernetes nowadays by default, right? But what you can do is rely on the MongoDB operator for MongoDB, for example. If you see on the screen, that particular example is MongoDB. So let's say you want to build a MongoDB database into Kubernetes. There's two solutions. You can do it manually, but then how do you manage the scale? So if you have a 3-node cluster, 3-node MongoDB cluster, how do you manage the scale of that cluster? Because if you build it with a stateful set, let's say, Kubernetes will manage the number of containers. So, okay, I'm going to increase my database cluster from 3 to 5 nodes, right? Okay, I'm increasing the number of containers. That's fine. But it doesn't it doesn't scale the application layer. It doesn't scale the database number of nodes. It just scale the number of containers, but not the application on top. So that's a perfect good use case for the operator. So if you look at the operator, the MongoDB operator, whether it's the enterprise or the community one, you will have a bunch of parameters you can manage by using an extension of Kubernetes primitives. So effectively, you end up with the definition of a MongoDB database natively in Kubernetes. So that means that when you create a database, Kubernetes will be able not only to scale the number of containers, but also take care of the database layer and also do things like backup and organize snapshots, do recovery, all those kind of monitoring, managing, user permissions, all those, management operation for your database can be achieved by using a database operator. So, and there are, I'm gonna stop discussing operator because this is not the topic for today. But if you go on operatorhub.io, you will find a lot of different database operators, and there are companies who specialize into creating those database operators, like Percona, or also every database will have an operator. So my advice is, if this is something that you consider because the argument of running your database in Kubernetes is appealing to you, then don't do it manually. Use an operator for that, and you will have probably to test more than one. So to finish up on that particular note, what are the pros of running your database, your database inside Kubernetes versus running it directly into the cloud? Right, by using a database as a service type of service, right? So here the idea is still the same. You want to deploy your database outside of your data center, but for Kubernetes, you're going to be running it in the cloud in Kubernetes. And for the second part, which is just consuming database as a service, it's running in the cloud, but the whole database is managed by the hyperscaler. So the pros for Kubernetes, you can save costs. How? We can go a lot deeper into how, but the idea is this one. So if you look at EBS or Google Persistent Disks, and in particular, if you want a certain degree of performance, if you want high performance, something like Reserved, it's called in AWS, reserved IOPS or reserved, can't remember the name, reserved IOPS, something like that, right? But where you need to have you want to have the guarantee that your drive can push that many IOPS, right? So usually it tends to be very expensive the larger you go, right? So the idea here, instead of using one large drive, you could eventually, depending on the solution you're using in Kubernetes, you can use more than one and build your volume by aggregating multiple EBS volume and writing, for example, in parallel to those drives. So potentially increasing the global performance while at the same time saving cost. So another approach could be, instead of using EBS or persistent disks, you could use instant store and ephemeral storage. Right? If you have the right CSI provider, then it doesn't matter if your node, the challenge with instant store and ephemeral storage is that if you shut down your VM, your node, then you lose your data on that node, right? But if you have a solution that is just constantly replicating, doing synchronous replication between your different volumes, your different nodes, then you're safe as long as you have at least one node running, right? So you can leverage instant store for highly performant workload at a fraction of the cost, because suddenly it's comprised into your monthly, just VM instant store cost. You don't have to purchase extra expensive EBS drive. So potentially you can save up to 3 times the cost you're spending in EBS. So you can do either cost optimization, multiple EBS drive, or you can do real cost saving by using ephemeral storage, which is another option. And I've seen customers dividing their bill by 200, of course, because you don't use EBS anymore, right? Another benefit is suddenly you can enable anything as a service by using the Kubernetes ecosystem, right? So now, as I said, the idea is to have Kubernetes as the cloud operating system. And that means that you can leverage all the Kubernetes innovation, can be fast, can be anything as a service that is operated inside Kubernetes as part of the solution, right? Of course, this means that you have this standardized across any cloud. And again, this can enable you, actually, it can allow you to avoid this vendor or cloud locking if this is something you want to do, right? Standardization. Now, of course, on the other side, we have cons. You can enable everything as a service for sure, but you need to learn, right, how to do it in Kubernetes. So there is still a learning curve depending on what you want to implement on top. You will have to learn new concept, new technology that runs inside Kubernetes. There is a higher maintenance and operational effort to do because, of course, now if you use a managed Kubernetes solution, the Kubernetes environment will be managed by the cloud provider, but you will be responsible for managing your database, upgrading your database, doing backup of your database. All that will have to be done. The operator, this is where the operator can help, but still, it's not managed by your hyperscaler. So it can be an advantage or it can be a cons as well, right? And the last one is how to enable premium data services, right? So imagine that you want to run your database in Kubernetes. Is what kind of solution can you use on top to provide, replication, encryption, performance optimization? All those things they don't come by default inside Kubernetes, right? And I think this is really what cloud native data is all about, is a combination of the cloud native features, which this is the one defined by the CNCF, essentially, right? Scalability, elasticity, self-healing, observability. Those are the qualification for running, compute in Kubernetes, and mainly for stateless application. For stateful application, again, it's a bit different. So we need to stack up a couple of requirements on top to be really efficient and being able to operate at the same level of availability that you would have by consuming database as a service like RDS, Bigtable, and others. So first, ideally, the storage should be distributed, not centralized, meaning that the Kubernetes nodes, if we really want to focus on Kubernetes data, then the data itself should be hosted in Kubernetes. So the storage provider should build the storage layer by leveraging Kubernetes nodes and containers, like essentially eating your own dog food. should be replicated, because if you lose one node, your volume potentially, if it's a read write once, needs to be available from another node, right? Other big requirements. Encryption, which is really important in the cloud, as more enterprise migrate sensitive data in the cloud, you need to get this data encrypted, and you need the communication from your microservices accessing this data encrypted as well. So in transit and at rest, preferably both encrypted. And you also need to have some sort of self-provisioning for your data as well, because as you move toward this idea of cloud native application and modern application, agile application, all of that, this is the notion of shifting left, which means that you want to test your application earlier in the development lifecycle. And as a result, your developers, they also need to have access to your data set early on. So you must be able to provide a way for your developer to copy, to provision, a set of data in Kubernetes on demand, and in a way that allows them to test, performance, to test, different things very early in the development lifecycle. That's the whole idea of shifting left. And finally, you also, question?
Yes. What kind of caching for database to be run as worker node, and how to do backup and restore databases in Kubernetes?
Okay,
so we're talking about availability, and so how do you do this? Yes.
So essentially, I would say caching database to be run. So caching, we don't change really the caching layer. So it's still at the application layer. That won't happen directly in Kubernetes. It will depend on your, you can have your database architecture. You can have Mongo and, MySQL and Redis on top, like this kind of thing. So it's really solved at the application layer, right? You make use of the caching. This is a definition in your application. It just happens that your application will be running in Kubernetes. And then how do you back up and restore? Again, part of it is can be managed by your operator, right? Before I've mentioned backup, etc., can be part of your operator, or potentially it can be part of your storage provider. Storage provider can have operational features. You can do now in Kubernetes, you can also have a leverage snapshot. So the CSI provider essentially can make use of Kubernetes primitives to guarantee snapshot, restore, and cloning. All of that are concepts that are already embedded into Kubernetes. So if you need this directly into the CSI, then you can use a CSI that provide this, or alternatively, there are dedicated solutions like Veeam, Kasten, and Velero that allows you to just back up your persistent volume your persistent volume, and allow you to restore them. So either embedded into the CSI, either from the operator, or like a more specific solution. Like there are three kind of ways to do it.
Thank you.
No worry. Okay, and the last one, DevOps friendly. So you want, as a requirement for your stateful application and your database, you want to have your DevOps tool also hosted into Kubernetes. So if we're talking about CI/CD, of course you can use GitHub Actions and whatever you're using. Or if you want to go cloud native and Kube native, you can use something like Tecton. You can use Policy as Code natively, something like Kyverno, to control the number of database cluster, replicas. This kind of thing can be managed by Kubernetes native DevOps toolsets. So I've mentioned Kyverno, I've mentioned Tecton. There's, you can apply GitOps principle as well with Weave, all of that without leaving the Kubernetes environment, right? So this is a good requirement as well. So now let's get a bit deeper into how to do it. We've seen why we want to do it in Kubernetes. We've seen the requirements, and now let's take a look at what are the steps that are really important to kind of migrate into Kubernetes. So first, what kind of volumes? Because the database ultimately will sit into a volumes into your Kubernetes cluster. So here I've typed a command for you guys. If you want to test it, it will give you all the volumes that are currently supported, which is a lot. They are a lot because there are also a lot of deprecated in-tree kind of volume drivers. So what I mean by in-tree, so prior to the CSI, which is the container storage interface, we're going to be talking about just in 1 minute, before that kind of standardization for plugins, all the current plugins that you have in Kubernetes, the storage plugins, were developed as in-tree driver, so directly into the Kubernetes main trunk. So every vendors had to do pull request and commit code into the Kubernetes source code directly. And this is why Kubernetes still have all those volume type. This was the kind of legacy way of doing things. Some are still required, and it's not completely, I think it's not envisioned to deprecate all of them, right? But the standard now, excuse me, is to use the CSI because that's a standard. So the main providers today, so persistent volume claim, most common one that is used through a CSI. This is mainly what you're going to be using for your database. MTDR, which is temporary file system, can be in memory or temporary on disk. Host path, which is a local path to your node. You can also mount as volume config map. Secret. Download API, which is contextual information about the pod. For example, the pod IP. Pod IP is not a bad example for volume, but for example, if you want to have access to annotation, labels, all of that can be mounted. All this information can be mounted into volumes. And also something a bit recent, which is ephemeral volumes, which is kind of the same as MTDR, but with extra components and also managed with CSI, and gives you another set of capabilities like limit the size, do snapshots, all of that. But where I'm going with this is nowadays, right, what you want to do is using the CSI driver, because the CSI driver is providing you with a bunch of extra features which are required to run production grade, I would say, databases. So things like dynamic provisioning and deprovisioning of a volume, right? You don't have to create the PV and the PVC. You can just create PVC, persistent volume claim, and then all the volumes can get dynamically provisioned for you. Things like, of course, attaching, detaching a volume from a node, mounting, unmounting, creating, deleting snapshot, provisioning a new volume from a snapshot. So you can see that all the new, shiny tools, shiny features that Kubernetes has been providing you for the last couple of years now, because it's 2018 for the CSI. All those new features are only available through the CSI. So again, kind of answering the question from before, if you need those extra, snapshot, backup features, all of that, you need a proper CSI to do this. So this is really the key here, right? Use CSI as much as you can, right? And then use the standard Kubernetes primitive, which are two ones, right? We have persistent volume and persistent volume claims. So persistent volume, this is effectively the volume itself. This is where the data reside. And we can see that there are essentially two ways to provision a volume, so persistent volume. Either you manually create a PVC, a PV, and attach the PV to the PVC, or you can use more dynamic provisioning or dynamic provisioning CSI. Every time you're going to create a PVC, automatically the CSI will also provision the backend persistent volume, which is a lot easier, right? So the idea, again, persistent volume, what you need to specify at the end is potentially, the storage class. You can leave it empty as well. It's the first storage class that is going to match, will be provisioning this for you. The access mode, the storage capacity, and then the name of the persistent volume claim, right? This is how you attach a PV to a PVC. You reference the persistent volume claim within the PV. That's one way to do it, right? And the second first class object will be a persistent volume claim, which effectively, as the name stands for, is claiming a persistent volume under your name, right? So with dynamic provisioning, it does two actions at the same time. It creates the claims and the volume. Here, depending on the solution you're using, this is also, for example, if you're using OnDat, right? That's just another example. This is where you can also manage the number of replicas. For other, storage provider, this is where as well you will be able to influence some extra features that are not available natively in Kubernetes. Still using the Kubernetes way of configuring things. So just by using labels, you can effectively enable and configure special features on top of your Kubernetes environment. So basically managing your underlying storage system by using labels, which is quite helpful, right? So again, here you you specify the access mode. So in Kubernetes, there are a couple of access mode, read write once, read write many, and we have read only many, and we have read write once pod, right? So typically, if you want a database, this is going to be read write once. Actually, this is just this picture here. The difference, read write many is for NFS, like shared file system, and read write once pod, as opposed to the other ones, which gives you like read write once. This is per node. You can write once, so meaning like the node will have access to a particular volume, right? That particular node will have access, will be building that particular volume for your pods. Now, if you have multiple pods running on that node, typically it will depend, if it's a deployment, then of course, if you have a deployment with read write once, which is a bad idea, only the first pod that is spin up is going to be accessing that volume, right? And the difference is that read write once pod, it guarantees that only that particular pod can have access to a volume, as opposed to read write only, which guarantee that only that particular node will have access to a volume, right? And nothing more. So that's the main difference. But here there's also, this part is confusing people. So how can you mount volume in Kubernetes? This is where you have the separation between stateful and stateless application. On the left here, this is a deployment, stateless application. On the right, this is stateful application, so a stateful set. On the left, in a deployment, when you create a Kubernetes deployment in the template, typically this is where you mount the volume. But the challenge is, because all the pods, when you create your deployment, all the created pod by the deployment controller will share the same volume, right? There's no other way to define it. In the template, you define one volume. So it means that all the pods deployed as part of the deployment will share the volume. So there's only one solution. That volume, if that needs to be a read-write volume, has to be based on a shared file system. So based on NFS. And you don't want to run a database on NFS because of performance, of course. So this is why stateful set is very important where you are running database or any stateful application. It's going to be using a persistent claim, volume claim template. So what that means is, instead of having all the pods getting access to the same volume, the controller, the stateful set controller, is going to provision individual volume per pods. So all the pods will have a stable name, right? Starting with 0. So my database -0, my database -1, my database -2. And this name will never change. If you delete the pod and create a new one, that will be the same pod with the same data attached. The PVC won't be, and the data won't be destroyed, right? So this is the reason why it's very important to use stateful set. And stateful set also requires a headless service, right? I'm not going to go in detail there, but the point is, if you're building database or stateful application, deployment and is not necessarily the right way to do it, except if NFS is okay for you, right? If NFS is fine for your application, you can do it. If you need more performance and one volume per pod, then you have to go stateful set, right? So, and on top of that, once you have chosen your right, Kubernetes native object to build your application or your database, you need to select your what is going to be your storage provider. So here again, we are talking about different patterns. So you can have on the one side you can be using a CSI that still basically is a wrapper around legacy storage, right? That's one solution. I wouldn't advise for this one. What we want to do is really build a Kubernetes distributed storage or container attached storage. This is the paradigm where you run Kubernetes storage within Kubernetes, and it's managed by using Kubernetes microservices and container. Again, it's like eating your own dog food, where your storage solution is going to be running as container and presenting storage to your application, database, all through your containers, right? So everything is container based, stayed within Kubernetes, is hosted by Kubernetes, and developed for Kubernetes. So a good example is Rook with Ceph. All the different components, the different agent, daemon sets, node agents, all of that is running directly into your worker nodes, right? So then you can go into a centralized model or a non-centralized model. It will be up to you. Another example is, on that, the company I'm working for, exactly same principle. You can select here, we have the different worker nodes, and you can say, for example, only maybe 2 workers will participate into the storage provisioning, into the storage space. All the other workers, they will be acting just for hosting containers as compute nodes. And depending on the solution, obviously you need to have like a protocol to allow you to get access from your application to your volume, still thinking the volume is local, but because realistically the volume is like, for example, here we have the application on one node, the volume is provisioned on another node, right? But from the application perspective, it's transparent. It still think it's a local bind mount, right? From a Linux perspective, it still appears as local. It just happens that the solution underneath provide a network protocol to get access to the storage, right? But realistically, this is still appearing as local storage, not as NFS storage. It's block device we are talking here, right? Still performance. Or you can say, okay, no, every node is going to be participating into your storage cluster and can potentially host data, right? That's the idea. So a couple of other solutions I've mentioned. Rook, which is a CNCF project that can make use of Ceph underneath. On that, which is formerly StorageOS, we have OpenEBS, has been acquired by Datacore. Portworx has been acquired by Pure Storage. Robin.io has been acquired by Rakuten Symphony. So as you can see, this is quite a trendy area where all the solutions tend to get acquired over time, and there's potentially a solution that fits your particular requirements here. So the only thing I wanted to do, like 5 minutes, is to show you how to do it within Kubernetes. So for this, I'm going to be using a quick GKE cluster. Let me share back my screen. There you go. So let's take a look at our Kubernetes cluster here. So I think it's a 3-node cluster. Okay, so as I said, the first thing, let's check. Yep.
If you can zoom in.
Okay, yeah. Sure. Better?
The fonts.
Yeah, I've increased the font.
Not yet. Okay, I guess. Yeah, that's good.
Yeah, okay. I'm not sure about the display because it may be,
bigger. You have bigger display.
Yeah, bigger. So it's going to be on the multiple line. Let's take a look. Okay. So we have the nodes there.
Yes.
Let's check the PVC. So I should have like 0 PVC at the moment. So what we're going to be doing, I'm going to show you first how to do it with pod, right? Natively PVC, create PVC, automatically create a PV, and then attach the PVC to the pod. like do this, and then how we can do it maybe in an easier way by just using a stateful set, right? So first off, we need to define the PVC, right? So I need to show you the storage class, because all that depends on the storage class, right? So the storage class will essentially tell you which CSI you will be using. So in Google, I was mentioning like so EBS like drive, like persistent disk. So Google persistent disk will make use of a particular CSI to provision your volume, essentially from a persistent disk, make them available into Kubernetes. This is how you can do this by using the Google CSI. Same thing in AWS. You can use the EBS CSI, and then dynamically is going to be provisioning PVC that are backed by and PV that are backed by EBS volume. So here I'm going to be using the this one, which is the persistent disk for standard read-write ones, and I'm going to be also using like the on that replicated ones. So let's first create our PVC. So this is standard read-write only. We want 5 gig, and let's just give it a name, PVC-1, and then PVC basic. Okay. So still pending. So why it's pending? Depending on the CSI you're using, if you have CSI that is topology aware, you need to wait for the Kubernetes scheduler to schedule a pod, and then the CSI will provision the storage that will be local to the node where the pod has been scheduled, right? So if you dynamically create, if the PVC is provisioned as soon as you create, so immediately, then what you may risk is that potentially, if the pod is scheduled on a node where the PVC hasn't been created, right, on another node, then the pod won't be able to get scheduled, right? So it's like a chicken and egg issue. If now you're using a CSI that doesn't care about the location, because it's providing like a network protocol to access a remote volume, then you don't care. But in the case of Google, this is topology aware, so we need to create the pod, and then the volume will be provisioned when the pod is scheduled, right? So for this, we create the pod, so we call it my pod 1. The only thing we need to do really is specify the claim name, right? This is PVC-1, which is the right one, and create our pod. Okay. Ending, but as soon now, if you monitor the PVC, it should be, it's bound now. It's bound because the pod has been scheduled on a node, and automatically the CSI has created now the PVC and the volume on the node where the pod has been deployed. So if I do now,
Nick, the storage class you have created, it was demanding for basically, it's waiting for a consumer.
Yeah, waiting. That's correct. This is here. This is where you have the difference: waiting for consumer or immediate, right?
Immediate, yes. Because even if you do immediate, and the BV, the persistent volume, has like an affinity to a certain node, it will work.
Yeah, of course, it will work. It will work.
But immediate, it will be a waste of time in cloud. So, I mean, why should you use the storage if the workload is not here?
It's not here. Yeah, totally. And so here the difference is that, so with the on that one, you can use both, but for some CSI, immediate is just not an option because it cannot really work, except if you have this, manual storage, a node affinity, these kind of things, right? Okay. So, so essentially now we have a pod running, and if you go exec here, my pod -1, and we have, just use bash here. I think that's /data. I can't remember now. Yeah, that's /mnt equals mount. Yeah, here, if I do touch test. Yeah, so I have a volume there. I've put some data in it. So we just checked it's been working, right? So we can do also the same with and on that volume now, and I'm going to just show you the difference. So here, the idea is to have a because there I've used Google, right? But the storage, except if you've been using a let's say a persistent disk that is regional, so potentially replicating between zones, your data is not replicated, right? So let's say you want to replicate your data, and for that you can be using on that, right? So on that, if you look at the storage class on that replicated, the only difference, if I do kubectl get storage class on that replicated dash o YAML, you will see that I've enabled the feature, right? Remember, all this is, whether it's on that or another solution, this is the kube native pattern. You manage the feature using labels and parameters, right? So here, the only thing I had to do to choose, I want to replicate all the volumes that will be provisioned by using that storage class, is this line, right? Number of replica, 1. I can go up to 5 if I want to, right? So now it's the same thing. I can do just the PVC will be here on that on that replicated, and I'm going to call it PVC2, and I'm going to create a new pod. We can hear you type so again, it's /mnt. Here I'm going to replace by this one, and I want also claim name. Remember, we have to adapt it to here. And now I'm going to deploy this new pod. Oops. Oh, sorry, I didn't create the volume. So we create the volume. Right. Okay, so if we look at the volumes, you can see the on that volume is already provisioned for you. Right. So here is already attached to the node, and we don't care, because regardless of where the pod is going to be scheduled, it can have access to that volume. And if I do a storage OS get volume, I will see the volume there, and I will see that it's also replicated one-on-one, right? So now let's provision the pod. Here we go. And here again, same thing, is going to be attaching the volume to that pod, right? And now it's running. If I do the same thing, again, if I do here, that's pod 2, set mnt, it also works the same way, right? So the only difference is now, of course, we will always try to collocate the pod with the node that has the storage attached. But now, if the node were to fail, dynamically the pod will be restarted on another node without losing access to that volume, right? If you do this in Google or in AWS in different AZ, that won't work. If you the node is another AZ, the volume won't be the pod won't be restarted, because the EBS volume is attached to a node that has failed. So if you want to restart it on another AZ, for example, you would need to replicate the EBS volume and attach the EBS volume to another node, etc., etc. So you need some sort of automation. With a solution like on that, it's totally automatic. We're not the only one. There are also other solutions that does that, but of course I'm working for on that. I'm showing you how to do it with us. And the last part I wanted to show you is, okay, I've done this with a pod, but that doesn't make a lot of sense, right? Because I don't have any controller that controls a pod. If the pod fails, then I'm screwed anyway. So what you want to have is a stateful set. So the properties of the stateful sets is this particular set of YAML lines that allows you to create a volume claim template. So you're going to see the difference. So now, so the only thing I'm going to specify here is the storage space. So how much, what the capacity I want, storage capacity, and the storage class. So here, let's deploy this, and you're going to see the difference. So as I do this, okay, if what it's going to be creating is three, if you look again at the STL configuration, is going to have 3 replicas, and all those 3 replicas will have individually a distinct volume attached to them. So now if I go, and the difference is also that, in a stateful set, every pod is creating sequentially one after the other, because they are pets, not cattle anymore, right? So the second one can be only created after the first one has been provisioned, right? There is this sequence that is there by default. So we have to wait. So already 2 has been created. Well, I should see 3 more PVC now, right? So you can see I've got now PVC1, PVC2. So here, my data, yeah, because it's it's a multi-line. The font is too big. But yeah, essentially, I've got 3 more. I've got my database, my STS-0, -1, and -2. So now I've got a higher level controller, which is my stateful set, and it is controlling the number of pods as well as the number of PVCs and how they are attached. If I was to destroy a particular, and this is why, for example, if I kubectl deletes a pod, which is mysts-0, right? The controller will recreate a new pod, but the data will still be there. The PVC doesn't get deleted. It's still there. It's going to be attached to the same one, right? If I get PVC, the PVC hasn't been destroyed, right? It's still the same one as before, right? 111 seconds ago, right? So essentially, this is the last part I wanted to show you. So just like a conclusion, I think we are a bit over time.
We are okay with time.
Okay with time. So anyway, I just want to share like the last couple of slides, and that's basically it. Okay, here we go. I think you have to add it again.
Oh, sorry.
That's fine, no worries. So yeah, what we've done here, we've been going through the provisioning of pods, PVC, attaching PV to PVC. We've been doing this with native cloud disk. We've been doing this with OnDats. The same would be available for another solution that provide extra feature sets for your data. The point is really to show you that, one, use stateful set, because this is the right construct to guarantee that you will have one volume per pod. Second, this is also the most of the time this is the construct that is used by Kubernetes and database operators. And also, again, to match the requirement we've been mentioning before, this is all about being able to provide features that are not enabled in Kubernetes by default. So database encryption, database replication, disaster recovery, all these extra feature sets. So in conclusion, hopefully the takeaway for today is Kubernetes is ready for stateful application with cloud native data. So if you are hesitating, you're like, okay, I want to migrate my data into the cloud. Should I do it by using a database as a service or natively in Kubernetes? Hopefully you've got some food for thought to give you options between both. You have some data to take into consideration, for taking your decision. But the key is to make sure that you can reach the right level of availability, recoverability, scale, and performance for the solution you're using. Remember, if you're using a platform as a service, database as a service, most of the time, disaster recovery, high availability is limited. One AZ or potentially multiple AZ, multiple region, but then you have to put the glue. With Kubernetes, database operator, you can stretch your cluster between availability zone. You can use topology key to make topology aware data. So there's a lot of solution that you can implement to increase the availability in the cloud by using Kubernetes and the appropriate storage solution. And finally, last point, persistent storage challenges are not addressed by default, right? So don't think that Kubernetes will tick all the box once you want to move production database into your cluster, right? Pick the solution that suits your requirements. So with that said, I've been more than thrilled to share with you all my thoughts for today. Hopefully it's been useful and you've learned one thing or two. I don't know if we have any other question, or maybe Wally, do you want to discuss other things like thought you had before, right? You're on mute.
We have some questions.
Okay.
There was one question from Khaldrad regarding the storage. Is it external or internal? Is it clustered or non-clustered? So basically, there is a confusion when you about the abstraction, the physical volume, and where is it consumed from?
Yeah, okay. So this is back to the difference I made between basic CSI and the CAS thing, so the container attached storage. So typically the CSI, so let's, if we start again from scratch, you have Kubernetes, you have CSI, and then you have Kubernetes objects, volumes, etc. The CSI is an abstraction for the volumes. So the volumes themselves, they can be pretty much anywhere, right? They don't have to reside inside the Kubernetes cluster. So for example, you can do Rook plus Ceph with an existing Ceph cluster. And the Ceph cluster is just a many storage node you have somewhere. What I'm trying to say today is not the Kubernetes way to do it. It's not appropriate for public cloud, right? If you want to get this, avoid the vendor locking and bring your own innovation, right, into your Kubernetes cluster and do this high, level standardization within Kubernetes, then it makes sense to turn Kubernetes into a hyper-converged solution and essentially building vSAN, so VMware vSAN, inside Kubernetes. And this is the latest set of solutions I've mentioned. So, Rook with Ceph, Robin, Portworx, Ondats, and Ioneer and others, this is what we are building. This is essentially all inside Kubernetes cluster and hyper-converged. And then you can choose where you want to put your data. Is it all nodes that are going to participate into provisioning the storage, or do you want to build storage node as opposed to compute nodes? But still, right, the storage is handled within Kubernetes. So my recommendation, if you're looking for a way to bring all this innovation with a pure, a standard framework, then yes, definitely use a CSI that gives you this ability to create the storage layer entirely in Kubernetes. And then regardless, you can have all the nodes provisioning storage or just storage node but you need to have, encryption, replication, all of that, make sure that you can also address those.
Okay. So the devil in the details. You don't have water?
What's that?
Water. Do you don't have some water?
See, whatever.
Okay. So the devil in the details. Now, when you say that Kubernetes democratizes the cloud, and I can have multi-cloud and I use Kubernetes abstractions, but I still, if I need to build my HCI, if I need to build my my HCI cluster that looks like a VMware vSAN, I have to use, for example, in Google Persistent Disk and AWS, EBS, I have to use the local node storage or storage attached to the node. Mm-hmm. Okay, so how does that work?
Okay, so in terms, again, different, all related to the CSI. Let's say you're using EBS, right? So your node will have EBS volume attached, right? So, and the EBS CSI will provision all the persistent volume within those EBS volumes, right, for your containers. So essentially, you attach an EBS volume to a node. The CSI will use that EBS volume space to provision and to create persistent volume that are subsequently attached to your containers. But the challenge with this, again, remember, the disk is attached locally to your node, right? This is EBS. So EBS are network attached storage. This is not device inside the node, right? This is network attached storage. And then what happens if the node fail? You need to attach. If you restart, if the pod is restarted on another node, the node needs to get access to that EBS volume. If the node is another availability zone, well, you need replication, and then you need manually or via an automation tool to attach that replicated EBS volume to the right node. So this is quite complex, quite convoluted. This is why you have other CSI like OpenEBS, like what we do at on that, because then you replicate. It's natively replicated at the Kubernetes layer, so that if the node fail, even though you have the EBS volume that is attached to it, the volume is replicated on another node, and that node also has EBS drive or EBS volume attached to it. It just happens that another solution is doing the replication for you at the Kubernetes layer, right? So basically, you have the data, and then you have an engine and the goal of that engine inside Kubernetes is to replicate that data, basically interfacing through the CSI. So you have the container accessing the CSI accesses the volume, and between the CSI and the backend node, you have this extra engine that does the replication. But again, then you have to think about, should I use EBS or can I make use of instant store, right? Because now the data is replicated across availability zone, etc. So the real question is, do you still need EBS? Because you can make use of the local storage, like the physical disk, the physical NVMe that are located into your nodes. So think about the performance. So EBS volumes, I don't know, like GP2, GP3, like 5,000, 10,000 IOPS, something like that. I don't know. If we're talking about NVMe, that's 5 times this, right? Or 10 times this locally on your NVMe. Plus, you don't lose the availability layer because your volume is still replicated at the Kubernetes layer, right? And even if you're using EBS, maybe instead of using like reserved IOPS, you can use GP2 and GP3 and combine them and aggregate them together with a solution like on that, rewrite personally on every disk you present us. So if you said, okay, I'm going to attach 3 EBS nodes, EBS volume to that particular Kubernetes nodes, solution like on that you create a PVC, and this PVC will act as a red 10 across all the EBS volumes. So essentially giving you more write and read power, right? More pipes. Of course, you're still limited by, if you do replication, this is synchronous replication, right? So you're limited by the network bandwidth, which will depend upon your instance size as well, right? So you have to be, there's a lot of parameters there, right? But the idea is that one. If you use a solution that uses EBS, maybe, and if you want high availability, EBS alone is not enough, in my opinion, because you need multi-AZ solution. Remember, like an AZ can easily fail. With EBS, well, you're a bit stuck. So you need an extra solution. Like Portworx, on that, whatever. And then with this kind of solution, then there is the second thought, which is, should I use OpenEBS? Should I use EBS volume altogether if I'm fine with NVMe locally on my instance, AWS instance? Yeah. Hopefully that clarifies things.
Yes. So a follow-up question from Khalid. What about live replication in active scenario? So I guess that's what you were referring to.
Yeah. So this is, I'm talking, so let me put different scenario here. For me, active is a stretch cluster across AZ. This is active. You wouldn't do active across region, right? That wouldn't make a lot of sense to me, just because of latency and everything. So it starts to be complicated to do active across cluster. So my advice, if you of course replication, like synchronous replication, single cluster, multi-AZ, use topology key. The good thing, like in AWS or Google Cloud, you can use, and others, you can use in the managed Kubernetes, the cloud provider, the hyperscaler, will dynamically populate the availability zone name in the topology key. So you will find like US West 1 or whatever inside the node topology key. And a solution like on that, as you know, I'm not sure about others. I think they do it as well, but we can use that topology key to place to create like initial volume placement and replication. So we can make sure that if you enable topology aware placement, that the replicated volumes are not in the same availability zone as the primary volume, right? This is how you do active by using availability zone as a topology key. This is one way of doing things. Now, for active standby, disaster recovery, then it's more about doing like snapshot replication into another cluster and recovering your application, let's say manually, into a new cluster. So you need to just your manifest redeploy them in your standby cluster or your test cluster or your recovery cluster where you share the load with other workloads. But the data will be there, right? If you can use this kind of solution. I know there are solutions that does this. Currently, I'm talking for on that. We don't have a like off solution for disaster recovery. This is in the pipes, so you can watch what we're doing by the end of this year. We should have this definitively. But yeah, this is active, which is synchronous, versus active standby. This is more like snapshot, asynchronous replication, and more manual things.
Okay. Okay, we'll do the random draw for the 3 KCN winners. So we'll select basically the first 3. Okay, the first time. Doesn't work. It works. I'm clicking on the wrong one. So the first one is Isa Nima. Okay, I'll get in touch with you, Isa, I guess. Okay. Congratulations. And let's do another one. Anurag Kumar. Okay, you are the second winner. And Saad Al-Shahri. Okay, thank you, Saad, Isa, and Kumar. I'll get in touch with you soon.
Nice.
Thank you, Nick. It was very useful and interesting. And
my pleasure.
We have some question regarding Rook, but it was answered during the call.
Perfect.
Other than that, there were questions about are we going to handle data security and data governance later on and stuff like that on future sessions.
Yeah, I mean, I would be more than happy to talk about policy as code. I mentioned it actually. I mentioned Kyverno and policy as code.
Yes.
I've done a couple of talk and things around Kyverno with stateful set and databases. I'd be more than happy to do this again. But yeah, definitely, again, Kubernetes is the right place to bring all those concepts, just as a way to innovate. So yeah, definitely.
Thank you again. Thank you, Nick. Thank you on that for providing us, Nick. And thank you, everybody that attended, and hope to see you soon. Thank you.
Thank you, everyone. Bye-bye. See you next one.
Bye.